Hi everyone, welcome back to Module 4. I know that with spring break we kind of maybe have forgotten about 4.1 and 4.2. So that's actually what this warm-up is going to do for you guys, is just kind of remind you about those. Feel free to skip through this part if you feel like you still remember, but this may be a good little warm-up for you guys to do. Today's lesson is actually going to be 4.4 and 4.5 because we're really only learning like the tiniest bit about 4.4. There's just one tiny thing that really matters. And then we are going to jump into 4.5. Okay, so let's do just a quick little warm up about 4.1 and 4.2. So if you guys remember, we have simplifying expressions and solving expressions. So the first one is to simplify. This is specifically with multiplication. So that means that you guys do not need a least common denominator. So that's not needed. That's only needed for adding or subtracting, and this is a multiplication sign. So the first thing that we are going to do is factor everything. So factor both numerators, both denominators, and then see if we can cancel anything, okay? So to factor this guy out would give us, that would give us x minus 5 and x plus 2. So that's this numerator. And that's over this denominator factored out is x plus 3 and x plus 1. So again, we got to be good at factoring. This numerator factored out is x plus 3 and x minus 1. And then this denominator factored out is x plus 2 and x minus 1. Okay, so that's every single thing factored out here. So these are equivalent. And then from here, we just look for things that we can cancel out. So remember that you can only cancel things out with numerators and denominators. So one on top, and it could be any of these tops with any of these bottoms. So right here, I automatically see an x minus 1 on top and an x minus 1 on bottom. So those can cancel out because anything divided by itself is equal to 1. I also see an x plus 3 up here and an x plus 3 down here. So that's top and bottom. So it could either be within the same fraction or different fraction because this is technically one big fraction. So those cancel out nicely. Let's see, what else can we cancel out? Looks like I have an x plus 2 on top here and an x plus 2 on bottom there. And whatever I'm left with is my answer. So number 1, all factored out and simplified, is x minus 5 over x plus 1. You guys can leave it like this, or you can keep your parentheses. It really doesn't matter, but that's your final answer. Okay, so that's simplifying with multiplication. And then let's do a solving one just to remind you. So for solving, we want that like magic trick, right? So we want every single denominator to be exactly the same. So we do actually want an LCD. So as you guys can see on this far left denominator, there's an x plus 1. This denominator and this one doesn't have an x plus 1. So we're going to multiply both top and bottom by x plus 1 for that middle fraction and this fraction. So now all 3 denominators have an x plus 1, right? If you guys notice, this guy has an x, this guy has an x, this guy doesn't. So we're going to multiply top and bottom by x. Now all 3 denominators have an x. And there's one final thing that each denominator doesn't have, and that's this times 2. So this guy needs to be multiplied by 2 top and bottom, and so does this guy. So now as you can see, all 3 denominators have a 2, an x, and an x plus 1. And what is that magic trick that we can do? We get rid of the fraction. All denominators cancel out, so we're only working with the numerators. Super nice. So this is 2x times 3x plus 6 times x plus 1. That's this guy. And that's equal to 7 times 2 times x plus 1. And then I can go ahead and simplify all of this out. So this is 6x squared. This can distribute, so that's 6x and 6. That's 14, and then go ahead and distribute to get to here. Then I'm going to move this guy over here, and this guy over here. There we go. Excuse me. And that leaves us with, this guy stays the same. So that's 6x squared. These two subtracted is 8x, and these two subtracted is 8, and it's all equal to 0. So then how do we solve a quadratic? We can factor it, we can do quadratic formula, or we can complete the square. The first thing I like to do is take out a greatest common factor though. So all three of these guys can be divided by 2. And because I have an equation, I can just divide both sides by 2. So that leaves me with 3x squared minus 4x minus 4, like that. And then this guy is actually factorable, so I'm going to go ahead and factor him. So if you guys remember, we do a times c, and then b, and what two numbers multiply to negative 12 that also add to negative 4? That's going to be negative 6 and positive 2. And then you can do box from here, you can do grouping method, you can do the AC method. I don't think I've done the AC method in a while, so let's do that. So what we do is we take this guy and put him here and here, and then we take these two and put them here and here. And then which of these can we basically simplify more? So this 3x and this 6 can both be divided by 3. So that leaves us with x minus 2 and 3x plus 2. So those are the factors of this. And then to solve, we're going to set each of these equal to 0. So for this guy, x is equal to 2. And for this guy, we subtract 2 and then divide by 3. So it's negative 2/3. And if you guys remember, we actually don't stop here. We do want to double check and make sure that there's no extraneous solutions. So we're going to go back to our original fractions and just make sure that if you guys plug anything into these denominators, do you get a 0? So if I plug in 2, I don't get a 0. And if I plug in negative 2/3, I don't get a 0 in the denominator because we can't divide by 0. So both of these are actually good. And those are our final answers. Cool. All right, so moving on to the actual new stuff of 4.4. So this is actually the only thing that we're going to do, just this top half. That's it from mod 4.4. That's it, okay? This is going to be a little bit weird at times, but basically rational expressions can be considered proper or improper. So let's first start to remind ourselves, what is a proper versus an improper fraction? So a proper fraction means that the numerator is smaller than the denominator, right? So for example, 1/4 or 2/3, okay? Or 5/12. So that's a proper fraction. And then an improper fraction is when the denominator number is actually greater than the numerator number. So for example, 3/2 is an improper fraction, okay? So we can apply that same kind of concept to rational expressions. So the way that we do that is we look at their degree. So for a proper rational expression, if the numerator degree is smaller than the denominator degree, it's proper. And then for improper, if the denominator degree is bigger than the numerator degree, then it is improper. So let's kind of go through all of these, and then we'll be able to move on to 4.5, okay? So this first one, this numerator, x plus 1, what type of function is it? What's the highest degree? Well, this is x to the first power, so wouldn't that mean that this is linear on top? Yeah, so just write x to the first. That's all I care about. I just care about the highest degree. Over, how about the denominator? What kind of function is this? There's x times x, which is x squared, right? So that would make this a quadratic. So do you guys see how the degree on top is bigger than the degree on the bottom? So this is a linear over a quadratic. So that would actually make this proper. This first one is proper. Okay. Now let's take a look at the second one. This guy this time, this was in factored form. This is now in standard form. So look at the numerator and what is the highest degree, the biggest exponent? Let me zoom in. What's the biggest exponent here? The x cubed, right? So that would make this a cubic. So it's an x cubed over, what's the highest degree of the denominator? A squared. So this is a cubic over a quadratic, and see how it's bigger on top, the degree is? So that would make this improper. Okay. Let's see if you guys can guess what the third one is. So do you think that this is proper or improper? If you got it right, it is proper because this is a quadratic divided by a quartic. So it's smaller on top, so it's proper. All right, now to give you guys a little curveball. By definition, look at this fourth one. What's the highest degree here in the numerator? A 1, so it's linear. So this is x to the first over, how about this one? Another x to the first. It's the same top and bottom. It's not smaller on top than bottom, and it's not bigger on top than bottom. They're actually equal. By definition of rational expressions, where does it say it? Right here. So rational expressions are improper if the degree is greater than or equal to the bottom. So if they are equal, it's actually considered improper. I know that's kind of weird to think about, but that's how rational expressions define them. So if they are the same degree on top and bottom, they are improper. Okay? So only if the degree is smaller on top is it proper. And then this last one, cubic, highest degree over linear. So it's bigger on top than on bottom, which would make it improper. So there's two different types of impropers. Either it's bigger on the numerator or they're equal. And then proper is smaller than the numerator. Okay. All right, so we are ready to move on to 4.5. And we are going to do the warm-up because today we're actually going to start to loop back towards 4.3, which if you guys remember, 4.3 was all about graphing rational functions. So we're kind of going to get back into graphing. So if you guys remember in 4.3, you learned how to find x-intercepts. You learned how to find the y-intercept. You learned how to find the domain And you also learned how to find the vertical asymptotes. So quick little reminder, of course, we'll go over this again. The x-intercepts, to find those. You set the numerator equal to 0 and solve for x. To find the y-intercepts, you make all x equals 0s and you solve for y. The domain, we actually like to do the vertical asymptotes first, so find those. So to find the vertical asymptotes, you set the denominator equal to 0 and you solve for x. And then the domain works off of, so you write it as an interval notation using the vertical asymptotes. So that's what we learned in 4.3. So one more graph feature that we're going to talk about today in 4.5 is the end behavior. So before we get into rational function end behavior, I want to see if you guys can remember end behavior that we learned in module 3 actually. Okay, so this is from mod 3. So let's see how we do. So the first thing you guys do is you look at the highest degree. So in number 1, what is the highest degree? What type of function is this? The highest degree is x squared. So that would make this a quadratic, right? So then what I had you guys do is basically picture, what does this quadratic look like? So if we rewrote this actually in standard form, this should go in front, right? So it's actually negative 3x squared plus 2x plus 7. So this is a quadratic, which is a parabola. And because there's a negative number in front, does this parabola face up or down? It faces down. That's what it looks like. So then what is the end behavior as x approaches positive infinity on the right? It's going down to negative infinity. And then what's the end behavior as x approaches negative infinity, aka the left-hand side? It's going down, also to negative infinity. Right? Do you remember that? I hope it's coming back. Let's do this one. So in number 2, it is a 5th degree is the highest. So if you guys remember, we based it on like odd versus even. So because this is an odd degree, it follows the end behavior of a cubic, right? It has the same end behavior of other odds. So because this is a positive 14x to the 5th, this graph end behavior looks like a rising cubic, right? So what's the end behavior as x approaches positive infinity, aka the right-hand side? It's going up. And what's the end behavior as x approaches negative infinity, aka what's happening on the left? It's going down, right? And then one more, just for good practice, number 3. So what's your highest degree? It's a 6. That's even, so that means it follows just like the quadratic or even a quartic shape. And then this is a positive value in front, right? So that means it's going to look something like that. So it's up and up. So the end behavior as x approaches positive infinity on the right is going up. And the end behavior as x approaches negative infinity on the left, it's also going up. So I hope you guys remember that because we're going to be talking about end behavior today for rational functions, okay? We still write it the same way, like this, but instead of using what I did, like a little sketch like this, we actually base it upon proper or improper. So end behavior of rational functions is based on proper or improper. Let's get into it. So the beginning of this task in class would have you guys take out Desmos or a graphing calculator, and in your groups you would discover what the end behaviors were. You're welcome to pause the video and do that, but I'm going to go ahead and just take out Desmos on my phone. Okay, so I just typed in this first one, this letter A, and it's 6 over x minus 2, which as you guys can see, it looks something like this. And actually looks very similar to what we graphed in 4.3, right? If you guys kind of remember doing those graphs. So if I kind of zoom out, can you guys tell, like, where's my end behavior? Like, where is my graph approaching? Remember, we don't care about the middle, just the left and the right. So where's it going on the right and the left? Can you guys tell? It's approaching the x-axis. So that means that this end behavior for this function, for this rational function, it's approaching the x-axis, which means that it's approaching 0. So for this first one, these guys are approaching 0. Okay, let me go ahead and type in the next one. Okay, here's the next one, letter B. So let's see, like, what is this approaching? It doesn't look like it's approaching 0 as quickly, right? Does it look like it's approaching the x-axis as I go towards the right? It doesn't. It doesn't get closer and closer to the x-axis, right? So instead, what is it getting closer and closer and closer to? So if that's 2, looks like it's getting closer and closer to that second line, right? Which if you guys look at the y-axis is 1. And the same thing's happening over here. Is this getting closer and closer and closer to the second box above the x-axis? Yeah, so this graph approaches 1. Interesting. Okay. Let me go ahead and put up C. Okay, here's C. Wow, this graph looks very different, right? So here's what C looks like. And again, we don't care what's happening in the middle, just look at the far ends. So what does it look like the right is approaching? You guys tell? This is like pretty much right there on the x-axis, right? It's getting closer and closer and closer to the x-axis. And is it happening over here too? Yeah, like that's approaching 0, right? Do you guys agree? So this graph, the end behaviors are approaching 0, or the x-axis for letter C. Let's go ahead and check out letter D next. Okay, so here is letter D. Again, kind of crazy, but let's just look at the far left and the far right. So it doesn't look like to me it's approaching the x-axis, right? It's not getting closer and closer to 0. It's getting closer and closer to a number pretty close to 0. So let's zoom in a little bit. So there's 2, so that means that 2 boxes is equal to 1 unit, right? Kind of go here. You guys see how this gets closer and closer and closer to 1? And then let's see if the same thing is happening over here on the left. This is coming down and getting closer and closer and closer to 1 as well. So it looks like this graph is approaching 1. Okay. Let's go ahead and see what's going on with letter E. Okay, so this is what I got going on for E, which is very interesting. Looks like pretty exaggerated here. But again, let's not focus on the middle. Instead, let's focus on the far left. If you guys can see, the far left basically just looks like a line that just keeps going down and down and down and down and down, right? Where's it going down to? And on the far right-hand side, there's this guy. It's just going up and up and up and up and up and up. So where's the far left going if it just kept going down? And where's the far right going if it just kept going up? Well, on the left, it just keeps going down to negative infinity, right? And on the far right, it just keeps shooting up to positive infinity. So that's E. Now let's take a look at F. Okay, last one here is F. Interesting. Kind of looks like a little cubic shape, right? So where is it going on the far right? Oh, nope. There's an interesting piece right there. So yeah, but where's it? We don't really care because that's kind of in the middle, right? So where's it going on the far right, this little guy? I just keep scrolling up and up and up and up, right? So that guy seems to be going up to infinity. And then where is the far left going? Well, this guy is plugged in like right around like 2, right? But I do have something on the left here. This parabola, if you guys can see, it's actually slightly more to the left of this guy. So that, this left half of the parabola is actually the far left-hand side of our graph. And that far left-hand side just keeps shooting up too. So both sides are going to infinity. So let's kind of look at our results. So let's try and see if we can pick up on any patterns. The first thing we're going to do is actually identify which ones are proper and which ones are improper. All right. So if we look at letter A, is this proper or improper? Down here at the bottom, that is a linear. Up here on the top, there is no x. So this is x to the 0 power. So that would mean 0 is smaller than 1. So this is proper. The letter A is proper. Letter B, we have a linear over a linear. So they're the same, right? So that would make this one improper, where numerator degree is equal to denominator degree, since there's 2 different types of impropers. Over here on C, this is a linear, x to the first divided by a quadratic, so it's smaller on top, which would make it proper. Okay. Letter D, we have a quadratic, 2 over a, x times x is another quadratic. So this is x squared over x squared, which means that this is improper, specifically where the numerator degree is equal to the denominator degree. Okay. Letter E, this is a quadratic divided by a linear, so it's bigger on top, which means that this is improper, where numerator is bigger than denominator degree, right? Degree. And then letter F is a cubic over a linear, so that would make this bigger on top. So again, it's improper, where numerator degree is bigger than denominator degree. So do you guys see any patterns? Take a look at the 2 propers. What were their end behaviors? 0 and 0. So guess what? Anytime that you're working with a proper rational function, its end behavior will always be 0. Okay? Then let's take a look at the impropers, which all look different, but these 2 are improper where they were the same degree on top and bottom, right? This was x squared and x squared. This was x to the first, x to the first. And they both had a number as their end behavior. It wasn't 0, and it wasn't infinity or negative infinity. It was a number, okay? And then this guy, the impropers where it's bigger on top than bottom, they were infinity or negative infinity. So it either went like up, up, down, 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 up, down. So this is the situation for rational functions. And how do we determine their end behavior? Let's kind of go down here. The numerator and denominator degrees have equal degrees. So that means it's improper where they're equal degrees on top and bottom. Okay. Let's actually start with this one, the proper. So what is the end behavior So as x approaches positive and negative infinity, what's your end behavior for a proper? Both propers were 0. It means that all propers will approach 0. What about if they had equal degrees, impropers? It was a number, right? They both were 1 though, which is interesting. So I do actually want to show you guys on Desmos a quick little different problem. Okay, so here's a new example. This is improper, where both top and bottom have the same degree, right? This is a linear over a linear. Now let's take a look at the graph and figure out what is the end behavior. Because for these two, we got 1, right? It doesn't look like the two ends are approaching 1. It doesn't, right? At all. Oops. Aha! Each box is 1. And I have to retype it. Hang on. There we go. So they're not approaching 1, right? So if each box is 1 unit, 1, 2, 3, 4, 5, what does it look like it's approaching? This is coming down to 3 boxes up, right? And then this one's coming up to 3 boxes up as well. So for this function, it approaches 3. For this one, it approached 1. And for this one, it approached 1. So where are they coming up with these values? Well, if they have equal degrees, what you do is you take the leading coefficient of the numerator and you divide it by the leading coefficient of the denominator. You guys will see me put LC for leading coefficient a lot in my work. So for this one, this was 1x divided by 1x. And what's 1 divided by 1? 1. Over here, this was 1x and 1 and 1. So what's 1 over 1? 1. In this problem, we have a 3x and an x, a 1. So what is 3 divided by 1? A 3. And that's what it's approaching. Okay, so that's how you guys find the end behavior of equal degrees. And then lastly, how do you find improper when the numerator is greater than the denominator? Oh, let me finish this one actually. So as x approaches both, f of x will approach, I usually write like leading coefficient divided by leading coefficient. So something like that. Okay. Now for this one, if you guys remember, these two approached either negative infinity, infinity, or infinity or negative infinity. So for these guys, it will always either be positive or negative infinity. Now, how do we distinguish if it is positive or negative infinity? Because that's really important. So for this one, you guys are very likely going to have to split up your end behavior instead of writing it like one thing like this. So if we look back, this is what you guys do. So you take the leading term in standard form. This is x squared, right? So you do x squared divided by, and this leading term is x to the first. What is x squared divided by x to the first? It's just x to the first, right? What does that graph look like? If I asked you to graph y equals x, what does that look like? Looks like that, right? What's the end behavior of this? On the left, it goes down. On the right, it goes up, which was the same thing here, right? So if you guys can break this down, basically divide it into its smallest function, that end behavior will match this one. So let's see if we can do letter F. So again, you take the highest leading term, which is 2x cubed, and you divide it by this leading term, x to the first. So 2 over 1 is 2. And what's a cubic divided by a linear? What's 3x cubed divided by x to the first? A quadratic. What does the graph of 2x squared look like? An upward facing parabola. What's that end behavior? The same one that we got. So that's how you guys find end behaviors of impropers when the degree is bigger on the top. So basically, you take leading term of numerator and you divide it by, notice how I'm putting leading term instead of leading coefficient. So you divide the leading term of the numerator by the leading term of the denominator. And then that end behavior is same as original. Okay. So next we are going to bring this all together. I just want you guys to try a couple. If you want more practice, you are more than welcome to get more practice. If you flip the page, because I know this has been kind of long, there are 1, 2, 3, 4, 5, 6 total practice problems. I want us to do 2 together. And then if you guys want to do more, you're more than welcome to, but you don't have to, okay? So let's do 2 together. So I'm going to have us do, I'm going to have us do number 11 and number 13, okay? And then, so that's just 2 problems. And then if you guys want to do more, you're more than welcome to. I keep pushing the wrong button. So here's number 11. And we are going to find everything, okay? So let's start with x-intercepts. So to remind you, you guys set the numerator equal to 0 and you solve for x to find x-intercepts. So we do 4x minus 1 equals 0 and solve for x. So if we add 1 to both sides and then divide by 4, our x-intercept is 1/4, 0. Okay. For the y-intercept, that's when you actually plug in 0 for all the x's. So 4 times 0 minus 1, and then 0 plus 2. 0 minus 1, because 4 times 0 is 0, is -1, and 0 plus 2 is 2. So that means that my y-intercept is -1/2. So we did this in 4.3, if you guys remember. And behavior, that's what we just did. So we first determined, is this proper or improper? So this is a linear divided by a linear. So if you guys remember, that's improper, but the degrees are exactly the same. So we're just gonna look at the leading coefficients. So 4 divided by 1 is 4. And then new to us, horizontal asymptote, that actually mimics the exact same thing as the end behavior. So if your end behavior is approaching 4, so it would look something like the ends come down. Like this guy might be like approaching 4, and then this guy might be approaching 4 this way. Doesn't that mean that we have a horizontal asymptote at 4? We talked about this in 4.3 as well. So that would mean that that's your horizontal asymptote. I do want you guys to write it like an equation, just like we did vertical asymptote. So horizontal lines is actually y equals a number. So for this horizontal asymptote, it's going to be y equals 4. So it's the same thing. Okay. Vertical asymptotes, that's what we did in 4.3. That's when you set the denominator equal to 0, and you do write it as an equation as well. So this would be x plus 2 equals 0, subtract 2 to both sides. So this is x equals -2 is my horizontal asymptote, sorry, vertical asymptote. I don't know why I boxed that one and not this one. And then finally, the domain, we use the vertical asymptote. So our domain stretches from negative infinity to this -2. And remember, there's not a bracket because it doesn't actually touch it. And then you guys can use a U if you'd like, or a comma. I don't really care. So then it picks back up from -2 to infinity. Okay. So that is number 11. And this is like basically all the features of graphs. So what we're going to do with our next lesson, 4.6, is actually put this all together and find out how to graph. Pretty cool. Okay. Okay. Really quickly, I do want to go back to this page and also talk about horizontal asymptotes really quickly. So as we said with this one, that's what we just did together where they had equal degrees. So your horizontal asymptote is y equals the same number, that leading coefficient over that leading coefficient. It's the same thing. For propers, also the same thing. They mimic your end behavior because that's what it's approaching, right? So it's y equals 0. This one, because it's not actually approaching a horizontal line, it's either going up, down, up, up, or down, down. It's not approaching a horizontal line. So in this case, there would be no horizontal asymptote because it's not approaching a horizontal line. Does that make sense? Okay. So we just did number 11 together. Let's now try number 13. And you guys will get more practice on homework as well. So here is number 13. So x-intercepts, we set the numerator equal to 0. And we solve for x. What's actually kind of cool is we can simplify this guy before we do any of that. So watch what happens when I factor this. Okay, so my numerator is 2x minus 1, and my denominator, if you guys were to factor this right now, you would get 2x minus 1 and x plus 3. And look what happens there. So this thing actually simplified is 1 over x plus 3. And that actually makes it a little bit easier for us down here. Okay. So our x-intercept, if it's to set the numerator equal to 0 and solve for x, is there an x to solve for? No. So that means that there's actually none. Y-intercept, we find the exact same way. We plug in 0 to x, which is a third. So we do have a y-intercept. That's a 3. And behavior, what type of rational function is this? I mean, it's going to be the same no matter which one you look at. It's smaller on top than bottom. So this is proper. And all propers approach 0. And because they're approaching 0, that also means that there's a horizontal asymptote at 0. Vertical asymptote is when you set the denominator equal to 0. So I'm going to set this new one equal to 0. Subtract 3 to both sides. So my vertical asymptote is x equals -3. And then finally my domain, which I'm going to use my vertical asymptote. So it goes from negative infinity to -3 and -3 to infinity. So those are all the features of a graph for rational expressions, rational functions. So if you guys want to stop here, that's totally fine. But if you need more practice, I'm going to put up the keys. I do want to put up the homework really quickly. So tonight's required homework is going to be RSG 4.5, and you're going to do all of them. And then for optional extra practice, if you guys feel like you want some more practice with like 4.1 and 4.2, you can do RSG 4.4 because that has a lot of good practice. But please skip numbers 8, 9, and 10 for 4.4. So this one's optional, but this one is required. So required homework is RSG 4.5, and this will be due on Tuesday by 4 p.m. So if you guys looked at that schedule that I posted Monday morning, it kind of gave you like an idea of what we're going to be doing. So let me kind of put one up for you guys. So this is like an example of an outline for the week. So on Mondays, you guys are going to watch a lesson. Tuesday, I'll have office hours for, this is just an example, but like on mine, for period 1, it's going to be 8 to 8:55. And period 3, I think was 10:05 to 11. You guys can double check my document though. And then the homework will be due at 4 p.m. Okay. And then Wednesday, you guys will watch the next lesson, and then office hours and homework will be due. And then we'll have some kind of an assessment on Friday. Okay. All right, so you can be done if you'd like, but I am going to put the answers up for these guys if you guys are curious. So for number 9, again, I'm sorry, I'm going to have it in pencil actually, because it's already done. So for number 9, we could have factored this first and those cancel. So there's your x-intercept and your y-intercept. And as you guys can see, it factored down to, like, after we canceled that out, this actually became, it's improper where it's bigger on top than bottom. So it came out to a linear, and this linear is an increasing linear. So that's why the end behavior on the left is going down and on the right is going up. Because we got this kind of end behavior, there is no horizontal asymptote, sorry. There's no vertical asymptote because we canceled that guy. And then therefore your domain, because there's no vertical asymptotes, goes to everything. And for number 10, here we are. So again, this is improper, but linear divided by linear. So you take the leading coefficient divided by the leading coefficient. That's why I got 3 and 3. That number will always match the horizontal asymptote. Vertical asymptote, set the denominator equal to 0, and use that to find the domain. Then number 12, if we factored both top and bottom, we had a cancellation here. So we had a linear divided by a linear, and that's why you guys see this 1 and 1. Okay, and then the last one on the back is number 14. So this is a proper, and we actually can't do anything with this numerator. If you guys set 4 equal to 0, you cannot solve for x. So that's why there's no x-intercepts, kind of like in number 13. All propers have end behavior and horizontal asymptotes at 0. That's why you see all the zeros. And then our vertical asymptotes, denominator equal to 0, and we match that with domain. All right, you guys have a wonderful day, and we will be doing 4.6 on Wednesday.